This is our lecture video for Quarter 2 Module 1 and our topic is about the unit circle. At the end of the lesson, you are expected to draw angle measures and determine the linear speed, convert degree measure to radian measure and vice versa, and illustrate the angles in standard position and coterminal angles. We will begin by illustrating the difference between the line segment, array, and a line. When we say a segment, this is a series of points with two endpoints. In this case, these points are the endpoint of this series of points. Speaking of array, array is a series of points with one endpoint and the other is extending infinitely. So this is the endpoint of our ray, and the other side of the ray is an arrowhead signifying an extension of these points. And lastly, a line has no endpoints. So in both sides of our line, it will extend infinitely. With that, in illustrating a line, we need to put two arrowheads. This time, we are going to define what is an angle. An angle is a union of two non-collinear rays with a common endpoint. Speaking of angle, we will be using two rays, and these rays are not collinear, meaning to say they are moving not in the same direction, and these non-collinear rays have the same endpoint. From the illustration, we have two parts of our angle, the initial side and the terminal side. The initial side is the initial position of our ray, and the terminal side is the position of the ray at the end of its rotation. And the common endpoint is called as the vertex. In trigonometry, we are dealing with an angle in a standard position. When can we say that an angle is in standard position? An angle is said to be in a standard position if its vertex is located at the origin and one ray, which is the initial ray, is on the positive x-axis. Remember, in our Cartesian coordinate system, we have two axes, the x-axis and the y-axis. An angle is said to be in a standard position only if the vertex is located at the origin. So in graphing that angle, our vertex is at the intersection of our x and the y-axis. Our initial side is located on the x-axis, that is on the positive x-axis. And our terminal side is located in any parts of our Cartesian plane. By that definition, we can say that the positive x-axis is the 0 degree of our angle. Our positive y is 90 degrees, our negative x is 180 degrees, and our negative y-axis is 270 degrees. Kindly take note that the measurement of an angle is determined by its rotation. If the rotation is counterclockwise, the angle is positive. And if the rotation is clockwise, the angle is negative. Remember that in our rotation, the initial side is always on the positive x-axis. So this is where we begin. So by rotating, we can determine the measurement of the angle. So if it is clockwise, if the rotation is clockwise, so from this axis, if the rotation is like that, the angle formed is negative. But if the direction of our rotation is counterclockwise, the opposite of the turning of our clock, so from this axis, so this will be the rotation of the counterclockwise. So if the rotation is counterclockwise, the measurement of our angle is positive. So for our quadrant, this is our quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So we will now consider the counterclockwise direction of our rotation. So what are the measurement of the angles found in quadrant 1? Since this is 0 degree and this is 90 degrees, all the angle greater than 0 but less than 90 are located in quadrant 1. The theta representing our angle is greater than 0 but less than 90. For our second quadrant, the measurement of our angle is always greater than 90 but less than 180 degrees. In quadrant 3, the measurement of our angle is greater than 180 degrees but less than 270 degrees. And for the fourth quadrant, the measurement of our angle is greater than 270 degrees but less than 360 degrees. So if our terminal side is located now on our initial side, this is equivalent to the 360 degrees rotation. Now, 90 degrees is located in what quadrant? Is it quadrant 1 or quadrant 2? The answer is neither of the two, because 90 degrees, 180 degrees, 270 degrees, and 360 degrees are quadrantal angle. The terminal sides of these angles lie on the axis. So if you are asked where can we locate what quadrant is 90 degrees, the answer is not quadrant 1 nor quadrant 2, because the 90 degrees fix the demarcation line between quadrant 1 and quadrant 2. In other words, we need to use 90 degrees as the reference in order for us to get what are in the quadrant 1 as well as what are in the quadrant 2. Also observe that in the quadrant 1, by definition, the angle is always greater than 0 but less than 90. And in quadrant 2, the angles are always greater than 90 but less than 180. In both quadrants, 90 degrees is not included in their jurisdiction. Let us now proceed to the lesson 1 example 1. Draw the following angle measures. In drawing the angle, remember that we are following the standard position of the angle, and you need to use the protractor in looking for the exact measurement of our angle. 45 degrees. Since this is positive, therefore, the rotation starting from the positive x-axis is counterclockwise. And by using the protractor, get the 45 degrees, create the terminal side, we have that angle in illustration A. For the angle measuring 400 degrees, look at the illustration in letter D. Since 400 degrees is positive, the rotation is still counterclockwise. And since this is more than the 360 degrees, therefore our angle goes beyond the 360 degrees. Remember that the one complete rotation is 360 degrees. Need to have additional 40 degrees to have 400 degrees. So get the 40 degrees on the quadrant 1, and that is our terminal side of the 400 degrees. For our negative 30 degrees, since this is negative, the rotation is clockwise. So from the positive x-axis, measure 30 degrees going to quadrant 4. So that is the terminal side of our negative 30 degrees. Drawing the terminal side of the angle is very significant in identifying the location or the quadrant of the angle. So for example, in 45 degrees, the terminal side is in the quadrant 1, so the 45 degrees is in quadrant 1. For our 400 degrees, the terminal side is still in quadrant 1. And for our negative 30 degrees, the terminal side is in quadrant 4. Kindly observe again the illustration of our 400 degrees. If you are going to draw the terminal side of 40 degrees, do they have the same terminal side of this 400 degrees? The answer is yes. They are called coterminal angles. Angles coterminal with a given angle theta may be derived using the formula. For our example, find 4 other coterminal angles of 410 degrees with n equals 1, -1, 2, and -2. First, let us compute the n equals 1. Using the formula, substitute the n by 1. So you have 410 plus 360 degrees times 1, which is 360 degrees. So your first coterminal angle of 410 degrees is 770 degrees. For our n equals -1, again, substitute the n by -1. So you have 410 degrees minus 360 degrees. So your second coterminal angle is 50 degrees. For our n equals 2, by substituting the value of our n, we have the resulting coterminal angle of 1130 degrees. And lastly, for n equals -2, we have -310 degrees. Therefore, by using this n, the 4 coterminal angles of 410 degrees are 770 degrees, 50 degrees, 1130 degrees, and -310 degrees. Since they are called coterminal angles, so if you will try to graph these 4 angles, they have the same terminal sides. The terminal sides of this angle are located in quadrant 1. For the exercises in finding the coterminal angles, kindly use the following values of n: -1, 0, 1, and 2. Let us now proceed to the conversion from degrees to radian measure and vice versa. Kindly remember this equivalent. The pi radian is equal to 180 degrees. So let us now convert degrees to radian measure, 50 degrees and 240 degrees. And we will be using the equivalence pi rad equals 180 degrees. So just copy the given degree. We will multiply the equivalence. Since the given is degree, we will be utilizing 180 degrees as our denominator, and the pi rad will be our numerator. We can cancel the degree, one from the numerator and the other from the denominator. Multiply now the 50 times the pi rad over 180, and this is the result. After that, get the common between 50 and 180. The greatest common factor between them is 10. So we will divide those number by 10. Final answer here is 5 pi over 18 rad. That rad is the shortcut term of our radian measure. Now convert the 240 degrees to radian measure. Again, we will copy the given. And since the given is in degree, our denominator should be the degree, which is the 180 degrees. And the numerator is the pi rad. So we have that 240 pi rad all over 180. And right after that, we will get the greatest common factor between 240 and 180. And the greatest common factor is 60. So we will divide 240 by 60. So this is 4. And 180 divided by 60, this is 3. Therefore, equivalent radian measure of 240 degrees is 4 pi over 3 radians. We will now convert radian measure to degrees. So we will be using this radian measure here, and we will convert them to get the respective degrees measured. We will first convert 5 pi over 18 radian to degrees. And since the given is in radian measure, so our denominator now will be the pi rad, and the numerator is the 180 degrees. After that, we can cancel out the unit radian as well as the pi. We will now multiply the remaining quantities by multiplying 5 and 180 degrees, so we have 900 degrees divided by, for the denominator, 18. So 900 divided by 18, the result is 50 degrees. Second given, 4 pi over 3 rad. We will copy first the given. and multiplying 180 degrees all over pi rad. Cancel now the pi as well as the unit rad. And we will now multiply the remaining quantities. We have 4 times 180 degrees is 720 degrees. For the denominator, we have 3 dividing 720 by 3. So we have 240 degrees. For your performance task in this week, each one of you will convert a 13-degree measure to radian. Kindly submit your respective solution in our group chat, and one group is in charge in consolidating your answers. Once that group is done with consolidating the answer, you are going to create a circle with the following degrees as well as its radian measure. So this will be your recorded performance task for this week. This performance task is the suspended performance task in quarter 1 about the circle. So you are going to illustrate in that circle the following degrees as well as the equivalent radian measure. We will now proceed to the linear and angular speed. This linear and angular speed is applicable in circular path or such as a clock. Formula for the linear speed is the arc length over time or S over T, and the angular speed is the central angle over time or the theta over T, where the S is the length of the arc, that is just a portion of our circular object, the time traveled which is our T, and the central angle theta must be in radian measure. So we have this problem. The second hand of a clock is 10.5 centimeter long. Find the linear speed of the tip of this second hand as it passes around the clock face. So what are the given in this problem? So we are given by the length of the second hand of the clock, which is 10.5 centimeter. Since the arc length here is in radian, so the entire clock represents the complete rotation of our angle. And remember, the complete rotation of our angle is 360 degrees. We will convert the 360 degrees to radian measure, and the equivalent of our 360 degrees is 2 pi. So for our arc length, we will multiply the radius as well as the radian measure of our clock face, which is the 2 pi. So we have the formula S equals 2 pi r. 2 pi times the r is 10.5. So our S is 21 pi centimeter. To solve for our linear speed, we need also to identify the time the second hand can pass around the clock face. That is the entire clock or the entire circle of the clock. So the second hand will travel the entire circle in 60 seconds. The value of our t in this problem is also 60. So by substitution, the linear speed is this. This time, we will be using the equivalent of our pi, which is 3.14. So we have 21 times 3.14, the product is 65.94 divided by the 60 seconds. So the linear speed is 1.099 centimeter per second. So what does it mean? So from our linear speed, we know that in 1 second, the second hand will travel 1.099 centimeter. And in the entire rotation, which is 60 seconds, second hand can travel the arc length of 65.94 centimeter. So meaning to say, the length of our clock from the outside is 65.94 centimeter. Let us try to compare this result by computing the circumference of this circle. Formula of the circumference of the circle is 2 pi r or pi d. So here, we will substitute the pi by 3.14 and the radius given is 10.5. Multiplying to 3.14 and 10.5, the product is 65.94 centimeter, which is the same with our derivation of the 60-second arc length or the entire length traveled by our second-hand clock. So, there is a connection between the linear speed as well as the circumference. Let us also try to involve the angular speed in this problem. For our angular speed, substitute the degrees 360 degrees all over 60 seconds. The result is 6 degrees per second. So meaning to say, second hand of the clock can travel an angle of 6 degrees per second. If that hand will travel the complete rotation, it can have a 360 degrees in all.